Hey, welcome back to ClearSpot. Here's a question that might keep you up at night. What if your solar farm is telling you exactly what's wrong, but you're not hearing it? Every string, every inverter, every sensor in your system is generating data. Voltage, current, temperature, power output, thousands of data points per second. Somewhere in that ocean of numbers is the signature of LID slowly stabilizing. The fingerprint of PID eating your capacity, the pattern of LTD creeping through your PERC modules, the thermal anomaly of a hotspot about to cause a fire. Traditional monitoring systems? They wait for thresholds to be crossed. By then, you've already lost thousands, sometimes millions, in revenue. Today, I'm going to show you exactly what each degradation mode looks like in your data, and how to catch it before it becomes expensive. Let's decode your solar farm's hidden language. Before we dive into each degradation type, let me give you the 4 weapons in your detection arsenal. Weapon number 1, string level electrical monitoring. This is your foundation. String monitoring units measure voltage, current, and sometimes temperature at the string level in real time. You're looking for current differences between parallel strings, voltage deviations from expected values, and power output compared to irradiance. When one string behaves differently from its neighbors under identical conditions, that's your first clue something's wrong. Weapon number 2, thermal imaging or infrared. Thermal cameras see what your eyes can't: heat. Every defect that affects current flow creates a temperature signature. Hotspots, bypass diode failures, PID damage, string disconnections, they all show up as thermal anomalies. Modern drone-based thermal inspections can survey an entire 50-megawatt farm in a single flight, capturing temperature data at each pixel with 0.08 degrees Celsius sensitivity. Weapon number 3, electroluminescence imaging. EL imaging is like an X-ray for solar panels. You pass current through the module in the dark and it emits light, but damaged areas don't glow. Micro cracks appear as dark lines. PID shows as dark cells near the frame. Manufacturing defects light up like a map. Weapon number 4, IV curve tracing. IV curve analysis measures the relationship between current and voltage across your string or module. The shape of that curve tells you everything about efficiency. The fill factor, how square the curve is, directly measures module health. Typical healthy fill factor, 0.72 to 0.77. Now let's see how each degradation mode shows up in these tools. Light-induced degradation happens in the first hours to days of operation. Here's how to catch it, and more importantly, how to know when it's done. What LID looks like in your data. During commissioning week, you'll see 1 to 3% power output drop that has nothing to do with weather or equipment problems. It's the boron-oxygen defects forming in your silicon. The pattern is distinctive. Day 1 to 3, gradual power decline under consistent irradiance. Day 7 to 14, decline slowing. Day 30 and beyond, stabilization at new baseline. The detection method. Compare your normalized power output, power per kilowatt per square meter irradiance, from day 1 versus day 30. You should see 1 to 3% lower output at day 30, and this is normal LID and stabilization, meaning the decline should stop. Red flags. If power keeps declining after 30 days under good irradiance conditions, you don't have LID. You have a different problem. LID stabilizes. Ongoing decline means PID, LTID, or equipment issues. Pro tip: pre-season your baseline expectations. If your manufacturer doesn't pre-treat panels for LID, assume 2 to 3% first-year loss in your performance model. Then your acceptance testing won't trigger false alarms. PID is the most dangerous degradation mode because traditional threshold monitoring misses it until catastrophic damage has occurred. Studies show legacy SCADA systems miss 68% of early-stage PID. Here's how to catch it early. What PID looks like in electrical data: PID attacks modules at the negative voltage end of your string. The first sign is string level voltage deviation. Look for open circuit voltage decline in specific strings daily average voltage deviations between parallel strings and voltage that doesn't recover after cloud cover or nighttime. Healthy strings recover their voltage quickly when conditions improve. PID-affected strings show persistent voltage depression. The math. A 50-panel string at 50 volts per panel should show about 2,500 volts open circuit. If one string consistently reads 2,350 volts, while parallel strings read 2,480 volts, that 5% voltage deficit is a PID warning sign. What PID looks like in thermal imaging. PID creates a distinctive gradient pattern near the module frame. You'll see cell-level heating at the negative end of the string, temperature differential emanating from module edges, and a pattern that's subtle initially but becomes more pronounced. One inspection company reports they can identify PID before it becomes visible in string monitoring or performance ratio calculations using high-resolution thermal analysis. What PID looks like in EL imaging. This is definitive. PID damaged cells appear as dark cells concentrated at the frame edge. The dark areas show where ion migration has destroyed cell function. Pattern recognition tip. Edge darkening in EL images is the hallmark of PID. If you see dark cells in the center of the module, that's usually a different problem, like microcracks or manufacturing defects. Early warning system. Implement daily voltage deviation analysis. Calculate the average voltage for each string over 24 hours. Compare strings in the same environmental zone. When one string's daily average starts deviating from its neighbors by more than 2%, investigate immediately. LTID is the hardest degradation mode to detect because, honestly, it just looks like normal aging. Only it's happening way faster. The real challenge is this. How do you distinguish a 6 to 10% degradation over 3 years from the expected degradation of just 1.5% over that same period? Both scenarios show a gradual decline in performance ratio, or PR. But here's what LTID actually looks like in your data. It creates a persistent, accelerating PR decline that just doesn't match normal degradation curves. So, what should you look for? In year 1, you might see a PR decline of 1 to 2%, which could easily look like normal LID plus routine degradation. In year 2, that PR decline keeps going at 1 to 2% per year, when it really should be only about 0.5%. By year 3, you're looking at a cumulative decline of 4 to 6% instead of the expected 1.5%. Now, here's the key insight. LTID accelerates in hot seasons and then partially recovers during cold seasons. If your PR shows a summer dip that's bigger than what temperature correction can explain, a winter recovery that's incomplete, and a year-over-year decline that's steeper than what your warranty curves predict, you likely have LTID. The detection method: use temperature-corrected PR tracked monthly for at least 24 months. Plot the trend line. If the slope exceeds negative 0.7% per year, remember normal is about negative 0.5%, you may have LTID. And you should always cross-reference with module technology. LTID primarily affects P-type PERC modules. If you have TOPCon or HJT panels showing this pattern, it's probably not LTID, and you should look for other causes. Here's the hard truth: you can't actually prove LTID from monitoring data alone. The only definitive test is accelerated indoor testing per IEC TS 63342. But your monitoring data can absolutely tell you which modules to test and when to file warranty claims. Physical degradation, like hotspots, microcracks, or bypass diode failures, creates the clearest signatures in your data, honestly. Let's start with hotspots, which are basically the cell-level alarm. A hotspot is when one or more cells are operating 10 to 20 degrees Celsius hotter than their neighbors. In thermal imaging, a single hot cell usually means there's a cell crack, shading, or maybe a manufacturing defect. If you see multiple adjacent hot cells, that's a sign of a bypass diode problem. And if you notice a temperature differential greater than 20 degrees Celsius, that's high priority and needs immediate action. Manufacturers consider anything over 20 degrees differential as evidence of a defective module that requires intervention. If it's below 10 degrees, you might just need to keep an eye on it. For differentials between 10 and 20 degrees, you should schedule some kind of intervention. Now, substring heating is what we call the bypass diode signature. When a bypass diode fails, the entire substring, typically 1/3 of the module, overheats. In thermal imaging, you'll see 1/3 of the module with a uniform elevated temperature, while adjacent cells remain at normal temperature. The pattern is rectangular, matching the substring layout. This signature means you've lost about 1/3 of that module's output, and it's only going to get worse. There's also full module heating, which is a bit counterintuitive. A completely disconnected module still absorbs sunlight but can't convert it to electricity. So all that energy just becomes heat. In thermal imaging, the entire module appears hot compared to its neighbors, and you'll see no electrical output from that module position. This is often caused by loose connections or cable failures. Always, and I mean always, correlate your thermal findings with electrical data. If you have a hot cell but normal string current, it's probably an isolated cell issue. If you have a hot cell and reduced string current, then it's an issue affecting output. A hot substring with a 33% current drop is a confirmed bypass diode failure. For further confirmation, trace the IV curve of any suspect strings. Physical damage shows up as a reduced fill factor. The curve becomes less square. And you might see steps or inflection points in the curve, which indicate multiple degradation levels. Lower ISC or short-circuit current with relatively stable VOC is another clue. Interestingly, the number of inflection points often matches the number of degraded modules in the string. Soiling is honestly the easiest degradation to detect, but it's often the most ignored until it starts costing real money. The reference string method is pretty straightforward. Install a clean reference module or use a dedicated soiling sensor. The sensor compares the clean module's short-circuit current to the soiled farm's average short-circuit current. The ratio between those two gives you your soiling loss. IEC 61724 actually defines this as the soiling level calculation. There's also the satellite comparison method. You compare your actual energy output against satellite-based irradiance data. Since satellite data doesn't get soiled, any divergence between the satellite predicted output and your actual output reveals soiling. Studies show this method can detect soiling within plus or minus 1 to 2% accuracy. So what does soiling look like in your data? You'll see a gradual linear decline in power output relative to irradiance. The effect is uniform across all strings, which is different from equipment failures. You'll also notice recovery after rain because soiling washes away, at least partially. It's usually worse in certain seasons, like during harvest dust, pollen, or dry periods. The economic decision point is key. Calculate your soiling loss rate versus the cost of cleaning. If you're losing 3 to 5% of annual production, the global average, and cleaning restores most of that, the return on investment for cleaning is usually positive. Now, backsheet and encapsulant degradation show up a bit differently. You'll see yellowing during a visual inspection and a gradual reduction in ISC without obvious soiling. Importantly, this isn't recovered by cleaning and is often concentrated in older modules within the same farm. If your power doesn't recover after cleaning and thermal imaging shows no hotspots, you should suspect encapsulant degradation. Let me tie this together with one simple truth. Every degradation mode leaves a signature in your data. The real question is whether you're equipped to read it. Let's break it down. Degradation primary. Signature best detection tool, allied initial power drop, then stabilization, commissioning baseline comparison. PID string, voltage deviation, edge cell heating, daily voltage analysis plus thermal LTD, persistent PR decline, beyond 0.5% per year, multi-year temperature-corrected PR physical localized hotspots, fill factor drop, thermal imaging plus IV curve tracing, environmental uniform power decline, rain recovery, soiling sensor, plus satellite comparison. Traditional SCADA systems that rely on threshold-based monitoring honestly miss the majority of early-stage problems. By the time those thresholds are crossed, you've already lost significant revenue. And this is exactly why AI agents matter. AI doesn't wait for thresholds. It learns what normal looks like for your specific farm, your climate, your equipment. Then it flags patterns that deviate from normal, even subtle deviations that would never cross a static threshold. At ClearSpot, we're building systems that detect PID voltage patterns 8 months earlier than legacy systems, automatically correlate thermal anomalies with electrical data, track LTID progression against expected curves, and prioritize interventions by financial impact, not just severity. Because here's the bottom line, your data already contains everything you need to know. The farms that win are the ones that actually hear what their data is saying. If you found this valuable, subscribe for next week's episode, Benchmarking Your Farm Against Industry Standards. We'll show you exactly where your PR, degradation rates and availability should be, and what it means if you're not there. At ClearSpot, we don't just monitor, we understand. Because in solar operations, understanding is everything. Thanks for watching. Like, share and subscribe for more solar insights. ClearSpot, smart device, smarter decisions.